days ago.
Power.
So you got two things to deal with. Ohm's law, which is V is equal to IR. And then we have the power equation, which comes in 3 flavors. And it just depends on which one is the most convenient one to use. Anyway, what do parallel resistors have in common?
Same voltage?
Absolutely the same voltage. So your best bet to answer this question is to find the one that has only voltage and no current. And then you can answer the question easily. What is the voltage that these 2 resistors have? 12. Square it and divide by those 2 resistors and we'll get our answer. If I'm talking funny, it's only because I got a face full of Novocaine and went to the dentist this morning.
Ouch.
1.2. Yeah, good. Interesting result, eh? What does that tell you? Nothing? Smaller resistors use more power. It's kind of an interesting little effect if you actually go and try to buy some resistors. The larger the resistance value, the smaller the resistors physically get. And the smaller the resistor values they get, the bigger, physically bigger they get. Because they have to account for the power issues.
Solve the power without using current. Yeah, it didn't.
Really surprising? Alright, there's another way we can put some resistors together. For the time being. Okay, so this is called series. We have two resistors, we have a 12-volt battery. That which is connected to the top side, the plus side of the battery, is 12 volts. That which is connected to the negative side of the battery is at 0 volts. And there's something between the two resistors and we don't know what it is yet. So we'll put a little question mark there and eventually see if we can find it. What is the voltage there? That'll be one of our goals. Okay. So the first thing we're going to do is figure out how to combine the two resistors in series. And this is quite easy. Our total is R1 plus R2. All you have to do is add them up. So how much resistance do we have? 150. Now that we know the total resistance, what is our total current? Any surprises thus far? All right. In the previous circuit with the parallel resistors, there were places where the current split up. So, for example, the current left the battery, came to this point, we'll call that a junction. Part of it went that way, part of it went that way. But now we've got a different circuit. And what comes to mind? Does the current split up?
The same.
It decreases.
Is there any, well, first of all, let's just deal with the splitting up. Is there any junctions? Are there any junctions?
Yeah.
There are no junctions. And that's one clear way to identify a series circuit. There are no junctions. So there's no place for the current to split up, which means that whatever the current is leaving the battery, that's the same current through the first resistor, and it's the same current through the second resistor. So the other thing to think about series circuits is that both resistors must have the same current. So it turns out in this series circuit we only have one current. It is the total current. It is the current through the first resistor. It is also the current through the second resistor. So I total is equal to I1, which is equal to I2, which is equal to 0.08 amps. Any questions about that series circuit and the current? All right, we know what the current is in each resistor. We know what the resistance is of each resistor. So let's find the voltage of each resistor. So V1 is going to be I1 R1 and V2 is going to be I2 R2. Prices there. All right, with those numbers at hand, how do I take this information and go back and answer this question?
Is that D1 or V2? I'm saying, is that V1 or V2? in this
Good
one?
question. Is it V1 or V2? Maybe it's both. Maybe you just average them. Who knows? Maybe something goes on. Any ideas? First of all, what about V1 and V2? If you happen to just be a compulsive adder, you notice that V1 and V2 add up to V initial. It's another rule. This V will always have to equal V1 plus V2. That will always be true. All right. So my favorite way of doing it is follow the zeros. So if I stay on the zero side, I know this is 0. And I know there's some voltage across this one. What's the voltage across R2? 8. So 0 plus 8 is 8. There we go. So that's 8 volts. Now there's another way to get there. You don't want 2 ways. One is enough. Just 12 volts. It's 12. 12 volts to here. What's the voltage across that resistor?
4.
But now you just have to subtract. So if you start on the high side, you're subtracting. If you start on the low side, you're adding. Yeah, 8 volts either way. Okay, both of these resistors have the same current. Well, that's the same question that I asked in the last set. Which one is using more power? They both have the same current.
Oh. V1 is right there.
Which one is using more power?
Yeah. So since they have something in common, we'll write down our power expressions. I squared R, E squared over R, which is equal to IV. Suggest for this comparison that since they both have the same current, it's useful to use the I squared R equation. P1 is 0.08 squared times 50. And in this case, since they have the same current, one of the larger resistance uses the more power, and they're in series. All right. No major surprises. We'll do one that's a little different. Okay, we got comfortable with 2 resistors, time for 3 resistors. And I got a 20-volt battery. And what does this thing look like? Is it parallel or series?
Both.
Both, yes, exactly, well said. It's parallel and series. Which part is the parallel? The 10 and the 50, R1 and R2 are definitely parallel. So you start there.
This might seem like a silly question, but how can you tell they're parallel? Is it just because they're next to each other?
No.
No?
It's a good question. How do you tell they're parallel? What you need to do is take a look at how they're connected. And the top of these 2 resistors are both connected to the top of the battery, correct? So if I were to write down the voltage, I would say this is 20 volts. This is going to be my 0 volts. I would say that that's 20 volts, and that's 20 volts. Write it so you can read it. So far, so good. That hasn't convinced me that they're parallel yet, but I keep going with this game here, and I draw the 0 volt side. And this is where my 0 ends. So 0 ends here. And I know that the lower side of the R3 is at 0 volts. And then I have that something in between. And we don't know what this is yet. But we do know that both resistors go from 20 to this unknown V. This one also goes from 20 to the unknown V. So whatever the voltage there is across those 2 resistors, they have the same voltage because they're going from 20 to the same endpoint of that unknown V.
They have the same voltage, yeah, but when the voltage is coming up, it's gonna be the same?
Well, they go from 20 to whatever this is. We don't know what it is, but it's the same for both, yes?
Mhm.
So they must have the same voltage across them. In terms of colors, they're both going from yellow to blue. It's kind of the advantage of coloring the lines.
But the resistance is different.
Well, resistance is different. They'll have different currents
Coming out of,
of going through each resistor, but they'll have the same voltage across them.
the input voltage is gonna be the same, the top one.
The 20
Mm-hmm.
and the difference between here and here, whatever that difference is. We don't know what that difference is. Why don't we write down what that difference is? I'm just going to write it as 20 minus V. So the language I'm using is that the voltage across the resistors is 20 minus V. In both cases, it's the same. Since they have the same voltage across each resistor, they are in parallel. While we're on this, why don't we write the voltage across R3, just like we did for the other two. How would you write the voltage across R3? Start with the blue and subtract the green. Pardon? V minus 0, right, exactly. V minus 0. Or just V. All right. Now let's take all that information and map it over to here. This is the same diagram, all I did is combine 1 and 2 in parallel. So that was a short detour to explain how we know they're in parallel, which was, I thought, very useful. All right, this is the result of adding 1 and 2. Now what does this look like?
A series.
A series circuit, right. So we'll recolorize things here a little bit. This is all at my 20 volts. This is all at my 0 volts. And that's at my unknown voltage. And so my strategy is to add these two resistors in series and find out what the total resistance is. Find our total. Then get I total. and then find the voltage across R3. Alright, I found out that the total resistance was 38.33 ohms. I found the total current in the circuit to be 0.522. Then I went back, and since there's at that point I3 has the same current, so I found the voltage across R3 to be 15.65 volts. Find out what is the voltage across 1, 2. Thinking about this, I've got 20 volts there, there's my 1, 2, there's my R3, found the total resistance by adding those two together, found the total current in the circuit, then I found the voltage across this one. What's the voltage across this one? Oh. Aha.
15.65 minus. It's 15.65.
What was that 15.65?
It's V3 that's going after the resistance there, right?
So what's the voltage across 1, 2?
Let me see that.
4.35.
4.35.
Oh,
The voltage across here is 4.35 volts.
yeah, we subtracted.
Voltage across here is 15.65 volts. we're gonna take that information and move backwards to our original diagram now. So what's the voltage across R2? And what's the voltage across R1? Also 4.25.
Yeah.
Is this the right current here? Because I'm using the current here. What? 0.522, right?
Question? So this is representing those two. So now we can find the current in R1 and 2.
Yeah, I agree. So, now I'm lost. Where are we now?
I feel. You and I both.
Voltage R3.
I wonder how he said default. You could do it.
I don't understand.
Like this, follow me. I know. We'll just copy them. Yeah, what are you doing? Oh, just barely.
So the V total will be 0?
Questions?
Yes.
So what is the voltage run to again on the picture?
Which picture?
Either one,
Either one.
because I'm blacking out on the.
What are we looking for?
When we say the voltage for 1, 2, 1, 2.
That's this
Which is the
right
V
there.
1, 2 right there?
This one is what
That's
represents
what I'm
this
missing. I
one.
don't,
Yeah.
I don't understand. How do you get the 15?
15.65? Where did that come from?
No.
Okay, so.
That's what I was gonna do right here.
Okay, so.
Find the total resistance, find the total current, and then find the voltage across R3. That's where the 15.65 comes from.
And then you just find the difference of the
They're between the V3 and the V12, right?
So you have to find this one zero. The difference between 0 and 15.
So that V question mark is that is voltage going to here?
And one more question before we leave it. Which resistor uses the most power? It'll take a little time to digest it. The good news is that they're not going to get any harder than this.
That's what you said last time.
Yeah.
That's what you said last time.
No, this is it. We're moving off of circuits after this.
Best thing I've heard all day.
Yeah, I think so.
The noise isn't quite making sense.
Well, maybe we'll do one more circuit for practice after this one. Then we'll move off. Which now you've got all the information because you know the current and the voltage
Oh, no, I'm
across
recording.
every resistor.
Oh yeah.
Do whatever you want to figure out the power used by each resistor and tell me which resistor uses the most power.
I am
currents, or use the voltages, or use whatever you like. Since we know everything about them.
Okay. So, not the volts for V3, that's like doing the equation right here. V3 is right there. So that's a 15 point, 15.6. Why is it 15? So this 0 and this V this here is 15. So now we figure out this voltage here is by 0 subtracting whatever voltage is in here. Is that what you're saying?
Did you use I2 R, I square R? Can we square this?
So
I
you're
used
saying
I
that the voltage
squared
for
R.
this
Yeah.
is in between the 0 there and
Yes. And then you do the same thing up here.
Those are the numbers that I came up with.
Use a different formula to get the same.
There's 3 formulas for power you can use, and since we have all the information for all of these, you can use whichever one you like. They should all generate the same numbers. Somebody getting different numbers? Oh. All right, one more circuit after this, and then we'll leave circuits. You got it all?
Yeah.
Not quite, right faster. Okay, make it simple for you. Find everything.
Find everything.
Everything. Find everything. So you have to know what everything is. But everything consists of, what is everything? All currents,
Let's see how this goes.
all voltages, and all power. current, voltage, and power for each resistor. And what are you absolutely sure about this circuit? It's a circuit, yes. Next thing that you might absolutely be sure about, R1 and R2 are in series. How do we know that R1 and R2 are in series? Not because they're on top of each other as much.
Because the volt has to go through one to get to the other.
Because the current has to go through one to get to the other. We know they're in series because there's no junction between them. That's probably a better way to say it. There's no place for the current to split between them, so they're definitely in series. So how do you add resistors in series? They're the nice ones you just added.
RT equals to R1 plus R2.
And 10 plus 50 is 60, right. Tried to make the numbers come out nicer on this one.
Where did you get the 60 volts from?
The battery. 60 right there. That's 0, that must be 60. And by the idea of the colorizing those things is to remind you that everything that's attached to that top side of that battery is also at 60 volts. Everything attached to the negative side of the battery is at 0 volts. So just by looking at that picture, do we know the voltage across any of those three resistors? Which one? R3. We know this one because it goes from 60 to 0, right? This one goes from 60, the yellow, down to blue, and we don't know what the blue is yet. We gotta find that. But we can at least use this one and we can get some current there, right?
So we're finding the current in that one, right?
We're finding everything.
So what's the R3 then?
R3 is 120. What's the I3?
Okay.
60 over 120.5.
Yep. I3 is equal to 0.5, 60 over 120 amps. All right, so we got half an amp there. What are we gonna do with those two beasts? We know what the total resistance is. Let's redraw our circuit. Maybe something will come to mind. We have 60 volts here. We now have R12, which is 60 ohms. We still have R3, with 120 ohms. Good. Green on this side. Yellow on the other side. Now we have a circuit with two resistors in parallel. We understand how to deal with that. Parallel resistors have the same voltage, and it's clear they do have the same voltage. They're both going from 60 to 0, 60 to 0. What's the current in that one? R12. Thank you. So now we found the current through this set. Then we go back to the previous diagram. So now we know that I1, I12, the current in that section is equal to 1 amp. How can I find the voltage of that blue segment? Try something. Take a shot.
Okay, so we're getting 60 volts. What's the volt in odd one? Did we find it or not?
Not yet, it's up to you. All we found was the current through R1 and R2. But how do I find the voltage of that blue section? You have a choice of ways of getting there.
Because I'm minute to think. Please have some mercy.
Mercy. No. No mercy. Sure, that'd be a great way to start. Current is 1 amp. Finding the voltages should not be difficult. So the voltage across R2 is 50 volts. Voltage across R1 is 10 volts.
How do you get the 50 volts?
V is equal to IR, Ohm's law. So we know the voltage across V1 is 10 volts, or the voltage across V2 is 50 volts. How do I find the voltage of that blue section? Add 50 to 0 or subtract 10 from 60. 50. That's at 50 volts there. All right. So far we should have all the currents. We have all the voltages. Let's just find all the powers.
You just get 10, right?
There we go, we got the power through each one. 10, 50, and 30 watts. There's really about 4 things you have to deal with circuits. You have to figure out, you have to understand what a parallel circuit is, what a series circuit is. You have to understand how to make use of Ohm's law, and you have to understand what the power equations are.
That's the end of the chapter.
Oh no.
I mean the circuits, at least portion of the chapter.
That portion of the chapter,
Okay.
yes. No, he put a lot in this one chapter. But I just want to just kind of summarize this stuff that we're doing with circuits before we move on.
It's good to know, yeah, what it's like. For V2, where's the parallel?
The difference between
So the formula, how to identify series and parallel?
Junction.
So you're saying you have to find one of 2 units track the voltage. So track the voltage going through. On this side of the resistor, yeah. Well, I got the current on that V line, it was 1. Watch for this one, you gotta find the current in the resistor with the gun. Right, now, where we on?
All right, so when thinking about parallel and series circuits, you know they're series if they have no junction between the resistors. sort of an easy way of dealing with it. Parallel resistors have the same voltage, and series resistors have the same current. There's your two series of equations, your Ohm's law and its three flavors, and your power equation and its three flavors. All right, questions before we leave this? Got it all written down, you'll digest it later on. Okay. Next little topic has to do with magnetic fields. Do you have any experience with magnetic fields? No? You live in one.
Earth's magnetic field.
Yeah, you're living in a magnetic field. There's a magnetic field that points roughly downward like that. Earth's magnetic field.
No wonder why I feel tired and hello now working because of the magnet.
The Earth's magnetic field, 0.5 capital G. Capital G is an antique unit, but still used. 0.5 Gauss. Yeah. The unit of magnetic field in the SI unit is called the Tesla. Nothing to do with the car. Right, yes. All right. Conversion factors. 1 Tesla, 10 to the 4 Gauss. This is kind of a mildly amusing relationship because Tesla is actually named after Nikola Tesla, who was a bit of a crackpot. He did some interesting things, but he was born, as they like to say, he was born broke and he died broke, but he produced billions for GE and Westinghouse along the way. Most of their inventions that Westinghouse and GE made their money on was from him. But Gauss was probably one of the most prolific mathematicians of all time, in at least Western history. So, one crackpot was worth 10,000 geniuses. One way to think about it. All right, what is the Earth's magnetic field in SI units? How do you use that conversion information? You're going to get good at converting one way or another.
We're converting to Tesla, how much?
Yeah, what is the Earth's magnetic field in Tesla if it's 0.5 Gauss?
It's times 10 to the power negative 4. Right?
Do something with it.
I'm done.
You're done.
Well, I was, yeah.
0.5 Gauss times 10 to the 4 Gauss is 1 Tesla. Which gives you 0.5 times 10 to the minus 4 Tesla. Or as it's more commonly written, 5 times 10 to the minus 5 Tesla. All right. Harmful effects of magnetic fields. There are no known harmful effects of magnetic fields.
No.
No? Therapeutic.
Even when it's high or higher than the norm.
I did have to work in a 13 Tesla magnetic field when I was doing my thesis. No damage to me, right? I wasn't hurt by it. No, there's no known magnetic anomalies to existing in magnetic fields. How about therapeutic effects? Go online, there's all kinds of little magnets you can buy to do everything from helping your power to think, helping your brain to think, to improving the circulation in your legs.
To be done.
They have magnetic beds, they have magnetic pillows. You can, there's a whole world of magnetic therapy. Any idea whether that magnetic therapy has any chance of working? What do you know that magnets do?
They manipulate metal, like it attracts metal.
Metal, all metal, or just some types of metal?
I would say certain types of metal.
Some types of metal. Any metal? Does metal have a name that you know of?
Like iron, it attracts iron.
Principally iron, yes.
Steel.
Steel, which is mostly iron.
Well, yeah.
Aluminum, no.
No.
No. Brass, no. But iron, yes. Iron is very strongly responds to magnetic fields. Is there iron in your body?
Yeah.
Where do we find that?
In the blood, the hemoglobin.
There you go. So maybe there is some effect of the increasing circulation. Who knows?
Screwed that up.
There could be some effect of magnetic fields on the body, but there hasn't been any discovered effects yet. Okay, so we need the Earth. Here's our Earth. And we are somewhere up here at about 37 degrees. There we are. And if you go down to the store and you buy a compass, a magnetic compass, where does that, well, who would buy a magnetic compass? You just have it on your phone, right? I don't have my phone with me. But your phone has a compass as well as GPS and everything else, right? So your phone can point you to the north. Well, if you use the compass feature on it, it will point you to magnetic north. Right. I'm not sure how your phone is figuring out what magnetic north is. I don't think they have a little built-in magnet on them. So they must be using GPS information to figure out what magnetic north is on your phone. That's a good question. How does the phone know where magnetic north is? But which way on this picture is magnetic north? Up, yes, the way we sort of normally, us northern hemisphere people tend to do it. We'll put our northern hemisphere up here. The Earth is rotating about its poles, and our magnet is going to point in a northwardly direction. And if we follow that along, we'll find that we get up to somewhere in northern Canada, and then our magnet just simply points straight down at the ground. And what happens is that this magnetic, what this compass does is it follows the magnetic field line, which goes through the Earth, and comes back out. There's another one on the other side. So these are magnetic field lines. Okay, now with that picture in mind, I want you to sort of think back to about the 3rd grade. Maybe it was the 2nd grade, who knows. But they gave you a little bar magnet. And our bar magnet had stamped on it north and south. And then they gave you some paper with some iron filings. Iron again shows up. And then what you found out when you were in the 3rd grade, and this was the big aha moment, was that there are magnetic field lines in the 3rd grade. And they do this business. Does that sound familiar? It didn't happen in your 3rd grade, you were deprived?
It may have it that's very vague.
Very vague. But you kind of get the picture of it now, if it looks like something you might have seen at the Exploratorium or someplace.
Yep.
There you go. Compare this picture to that picture. Compare and contrast, as I like to say. Frustrated English professor. Compare and contrast any two things. They're opposite? Opposite. Something, I drew something wrong here. Yes, sorry, I drew something wrong.
Isn't it always north or south?
I'm upside down.
That's what I thought, but I'm like,
One is
no,
right.
I don't know what I'm talking about.
That one is wrong. Talking and writing gets me into trouble. That's what I wanted to say. Now we can compare and contrast. Similarities and differences. The direction, what do you mean by the directions are opposite?
Oh, those are the fun ones.
From the north, one is coming out, no, both are coming out from the north. We're supposed to
So in the bar magnet, what you saw in the 3rd grade, you were sure that they were coming out of the north. And now you're sure that they're going in at the north. That's because the north pole is a south magnetic pole.
Oh,
This is actually south and that is actually north. Now does it look right? So when we think of the North Pole, it's actually a south magnetic pole. Geographic north is south magnetic. And geographic south is magnetic north as far as the Earth goes. So our little compass that we bought at the hardware store, its little magnet lines itself up with the lines and they will plunge into the Earth at the North Pole roughly. That's equivalent to our little magnet following along this line and coming into the South Pole. Any other differences, especially in the way I drew these two cases? Similarities, differences.
So we found the difference so far, right?
Well, you found something. It's really more of a similarity that we found. We found out that yes, the magnetic field lines leave the north and they come in on the south. They leave the north and they come in on the south. That's a similarity. Although we had to identify the geographic north as the south magnetic. I'm looking for one other difference.
Like each of the hemispheres going along the outside, so you
They're both, that's a similarity. This one's going around the outside of the Earth, this one's going around the outside of the magnet. Follow up on that just a little bit more and you,
Well, then each side is doing.
each side is doing it, yeah. But there's just, it's something about the way I drew it, which looks innocent, but it's actually significant.
I think on the right one, the north, the south is going west.
Okay.
Well, it's going into the south. We don't care about the east and west in this
On
picture.
one side, it seems we have more power for the magnitude field than the other. It's larger.
There's a slight difference in the way I drew it. That's not what I'm trying to get at. It's a big, really big difference.
One's
between this-
horizontal.
No, that's close, but no. It's almost as big as that.
It's a type of that.
The shape, different shapes.
Not quite the shape.
Not the size.
Okay.
Line all the way through.
There you go.
Got it.
I drew these lines all the way through and around. And when you were in the 3rd grade playing with your iron filings and the paper and the magnet, you couldn't see the magnetic field lines inside the bar, could you? But it turns out that magnetic field lines do not end. So they always connect all the way through. And so actually, magnetic field lines point from north to south outside, but they point from south to north inside. They didn't tell you all of that in the 3rd grade. So magnetic field lines don't end was the important statement that I'm going to end on. And if you ever do find a magnetic field line that does end, you can get a Nobel Prize. We've been looking for that for the last couple hundred years. And they still look for it. All right, great place to stop. And finish up your corrections to your electric force calculation. Most of you just have small little things that you overlook.
Is it possible you could find
I screwed up so many times.
Yeah.
I was laughing.
I think you nailed it.
Oh, thank you.
Yeah.